hopefully worked out. I didn't check this morning to see if it did, but I assume it did. That should have been released to you all at 6 o'clock last night. And I'm seeing some heads nodding, which is good. Hope you had a chance to take a look at that. Let me make a few comments about it first, and I'll very happily take any questions you might have about that. So, as you've seen, if you've looked at the midterm, you've already seen there's 3 problems on there. You'll notice those 3 problems fall right in line with what I said they were going to be. We have a problem which is nothing more than 3-by diagrams. We have a problem that is a machines type problem. It turns out both those problems are related to each other. So one is just do the 3-by diagrams and don't worry about solving it. The second one is solve it using the 3-by diagrams that you created. And that's an important thing, folks, you need to understand. The concern could or should be that, well, if I get the 3-by diagrams wrong, doesn't that mean I'm automatically going to get the solution problem wrong too? Doesn't necessarily mean that. I did this on purpose. I'm going to use whatever you did for your 3-by diagrams to guide the thinking on, well, how did you solve it? So if there's a mistake in your 3-by diagrams, well, that's the mistake there. But if you properly propagated that mistake through the solution, well, that's okay. In other words, your solution is correct to your 3-by diagram. So done purposefully so that it doesn't create any penalties, all right, any penalties. Now keep in mind, if it goes the way it should, you're gonna focus your energies on really making sure those 3-by diagrams, and as you should have seen by now, it's a pliers type problem. There are 4 elements on that, and in doing those 3-by diagrams, there is nothing new here, folks. The thing I'm going to be looking for is that you remember to follow all the steps in the recipe. Did you draw those 4 elements completely isolated from each other? Did you include a coordinate axis system? And you know what? If you're drawing 4 3-by diagrams and you include 1 coordinate axis system, well, you're fine. That's good enough. We don't need 4 of those, but at least there's something there. So 4 diagrams, 4 coordinate axis systems, forces that are applied. The problem says specifically you don't have to worry about weight. We can neglect the weight of these things. Everything's smooth, by the way. Everything's smooth, including all the pins. They're smooth. The applied forces, and then most importantly, and folks, lean in and hear me when I say what I'm about to say. The thing that I will be looking for, and the mistake that I don't want you to make, is if you drew, for example, let's say you drew on one 3-by diagram a force for, let's say, pin C. Let's say you draw a CX going that way on one of your 3-by diagrams. Then where CX shows up on the other 3-by diagram, whatever was connected to that, if CX is going this way on that one, it's going to be going that way on the other. The equal and opposite thing. And I say that and I stress that because, folks, just in all honesty, that's the thing that usually gets forgotten, and it can't be forgotten. So I'll be looking for that very specifically. But when you're done with that, don't leave problem number 1 until you can look at that and say, I am confident I've got those 3-by diagrams right. Folks, again, and listen to what I'm saying right here. If you do problem number 1 and you don't feel confident that you've got those 3-by diagrams right, you got a choice. You can either roll over and accept it, or you can say, I need a hand here. Reach out to me. Ask questions. Don't feel bad about asking questions. I would so rather help you get it right in the first place versus try to figure out how to undo it after you got it all wrong, right? So again, and I hope you're hearing me, I will feel very displeased, I guess is the right way to say that, if you turn in a midterm exam that's got a bunch of messed up 3-by diagrams and you didn't even bother to ask. That's just not the way to play. All right, so let's make sure we do that. Don't leave problem number 1 until you really feel good about those 3-by diagrams. Now, that's not to say that, here's one thing I can't do, folks. I can't, if you email me and say, hey, here's what I'm thinking for my 3-by diagrams, can you tell me if I'm right? Can't do that. right? You can't do that. I can't even tell you if you're on the right track. I might say you're on the right track, but that's as far as I will go, right? But you can certainly ask specific questions. I'm not positive about how to represent this force, and I'll give you some insight on that. You know, something like that. But don't not do that. So now, if you've done that and you focus on problem number one, you feel really good about your free body diagrams coming out of problem number one, then problem number two just simply becomes figure out how many equations of equilibrium you need to solve the problem. Folks, I will tell you that when I solved the problem after I put it in the exam, I did it in 2 equations. That's not to say you might not need 6 or more, I don't know. But it is possible to solve that in 2 equations. So just know that. But again, that's not the goal. The goal is not to say, okay, you heard Professor Hargrove say 2, I need to do it in 2. No, you don't. You just need to do it in however many equations you need to get there. That's really it. And then after that, we got problem number 3, which is the trust problem. And as I said, the trust problem would be, it states right in the problem statement, using any method you choose. That problem is solvable using method of sections. That problem is solvable using method of joint. I will say this, and I'm going to say this in a 330 class as well. There is something that if you notice something unique about one of the members, that's going to make this problem super simple. If you don't notice that something unique, it's just same old problem. There's nothing, it doesn't change anything. It's just one avenue makes it ultra easy, one avenue makes it easy. So I'll say that. I will also say this. In the period of time that you've got to complete this exam, which, let's be clear, you've got 8 days, right, to do a 1-hour exam. Even though problem number 3 is saying use any method you want, doesn't, like the voice of common sense that whispers in our ear, it should be screaming right now, doesn't that say, well, you know what, I might try doing it with method of sections and see what I get, and I might turn around and do the same thing with method of joints and see if I get the exact same thing. Because folks, if you use both, now I'm not saying I want you to do that on your exam, because that just makes it confusing for me to, evaluate it. But if you use both methods and you get the same result, boy, would I feel good about my outcome. If I use both methods and method of joints is saying one thing, and method of sections is saying something else, then I wouldn't feel so good about that. And we're talking about, what, an additional investment of, 15, 20 minutes to try to, make sure you get it right. So I would encourage you to do that, folks, just to make sure. I mean, it's a wonderful fail-safe to make sure that you've got an outcome that makes sense, that's realistic. Morning? Morning. Let me think, what else will I tell you? On those problems too, as is always the case, it's really smart to just kind of think about like what you expect the outcome to be. Take the pliers problem, for example. If I remember right, the pliers problem has 150 newtons being applied to the handle. We're trying to figure out how much pressure's being applied or how much force is being applied to the smooth ball bearing that's in its grips, right? So think about that, folks. The way those things are designed, obviously those kinds of tools are designed to amplify the force. So if I'm putting on 150 newtons, I would expect my outcome at the business end of that to be a lot more than 150 newtons, right? So the question becomes, well, what's reasonable? Is it 2 times, 5 times, 10 times, whatever? All those are reasonable. On the other hand, if anybody thinks that if I apply 150 newtons, I'm going to get 16 quintillion newtons on the, on the outcome of that, well, that's not reasonable. Or if you apply 150 newtons, you're going to get like 0.2 newtons on the outcome. That's also not reasonable. So, look for those kinds of things in your answer. If your answer says, hey, it's 5 times more, then boy, that's reasonable. If your answer says 10 times more, boy, that's reasonable. That's very reasonable. And I'd feel good about that. Something to think about. Now, as a reminder, and I hope you're all hearing me clearly when I say this, the exam is due a week from today at the beginning of class. Right? So the first thing we'll do a week from today is I'm going to collect the exams. We'll talk about them after I've collected the exams. You've got to bring a hard copy. And somebody asked a question, it was a good question. Last time we talked about this, does it have to be a printed copy of the actual exam, or can it just be like, hey, I wrote my solutions on 3 pieces of paper, here you go. I'm good with either, but with caution. If you choose not to print the actual exam, you got to give me the info that I need to be able to solve or to assess your problem. So, you know, replicate the diagrams and stuff like that. So your call, I don't care, whichever one, you know, works for you. I did actually add, I think, a statement on at least one of the problems. I can't remember which one it was, but I said something to the effect of make sure your arrowheads are clear, or something along that line. I'm going to tell you why, folks. I'm going to tell you why I did that. I've had recent times being, you know, in the last couple of years, where folks will turn in something and they'll have forces and the arrowheads will look like that. All right? Seriously, look like that. And now the question becomes, is that arrowhead right there pointing down? Or is that arrowhead pointing up? Or is that the end point? There should have been an arrowhead up here. I have no idea. None whatsoever. I think that might be some sort of a play, like, hey, maybe if I make it ambiguous, I can argue that that's what I meant on the back end. Well, if you think for 2 seconds I'm buying that nonsense, think again. So all I'm saying is, if you're going to draw an arrowhead, make it obvious what it is. I'm not going to guess, and trust me, if I have to guess, I'm going to guess against you every time. So make sure to do that. I'm just trying to think, is there anything else? One person asked me in the 330 class, like, how many units do I want you to carry the calculations out to? Honestly, I don't care. That units thing is something that's been way overly blown out of proportion for years in our world. You know, a couple decimal places, I'm happy. If it makes sense, round up to the nearest unit or integer, I'm perfectly happy. In fact, I'll tell you this much: 150 newtons on that handle of that pliers, 150 newtons applied. If you give me a response that's like round to the nearest integer, cool, I'm happy with that. What doesn't make sense, this is again pure logic and common sense right here. You got 150 newtons squeezing on something. If your answer works out to be, and I'm just making up a number here, 865.209073222 or something like that, all that stuff on the back end of the decimal is irrelevant, right? So again, I just don't care about stuff like that, so don't worry about that. If you feel good with a couple of decimal places, fine. If you don't want to do that, also fine. The logical question that comes up after that, though, is, but my answer may be a couple of units different than yours because I rounded differently. Yeah, so I'm not going to, we're not going to mince meat over that. So, as long as it's in the ballpark of what it should be, all's good. So don't worry about that. Let's see, what else? Folks, I will say this too. If your style of handwriting is that you kind of prefer to, make really small letters and stuff like that, just know, think about this, and this goes beyond just me. Anybody ever grading any exam or anything that you're ever going to do in your college career, the last thing you want to do is put them in a bad mood when they're grading your stuff, right? So there's nothing that puts me in a bad mood worse than I got to go get a microscope to see your handwriting. So make it a little bit clearer if you don't mind. That would be really helpful. Otherwise, like I said, bad mood equals trouble for you. So I'll say that one as well. Gosh, I think I've run out of things to talk about as far as that exam goes. How about you? What questions have you guys got on the exam, or did I cover everything? Anybody, please don't wait. Please don't hesitate. Listen, hear me. I don't know if I said it to you guys, but I know I said it to my 330 class because I thought of it then. If I said it to you guys, I'll say it again. I'm asking you right now for questions about the midterm exam. If you have none, and then wait till I'm done with lecture and then come up here and say, hey, I got a question about the midterm, I will thank you and tell you I'll talk to you some other time. I'm not going to answer any questions about the midterm after lecture today. So if you have them, now's the time. Anything, anybody? Cool. All right, real fine. Let's go to work. Check that out. We are now moving into the world of machines, and oh my goodness, is there a question?
Yes. What would be the setup for problem to ball bearing? How would you set that up?
Tell me more. I have no idea what that means. How would I set that up?
So like, you're using a ball bearing, so you're using the
forces on that? Yes, good question, great question. So the key word there was smooth, right? And I want to go back to, well, think of it this way. If I had a ball bearing in 3D world, I see a sphere, right? A ball bearing in 2D world is just a circle. So it's just a roller. That's all it is. So if you think about a roller, we know that there would be a normal force against the plane of contact. And if it's smooth, we know there'd be nothing that way. So it's that. It's a great question. I appreciate that one. That's why I want to ask questions, folks, because I hope everybody just heard that. You all, I'm going to come to you in 2 seconds. You all are looking at that exam right now, thinking, I'll figure this out later. You wisely said, I want to know right now. That's smart. So those are the kinds of things, when you look at the problems, you're going to have to ask yourself eventually. So look at it now. And if you see something like, I'm not sure how to do that, ask the question what you have.
So the ball bearing is in contact on 2 surfaces, would that be 2 normal forces?
Depending on your 3-by diagram. Great question. So very, very good question. Now notice here, I didn't ask for a 3-by diagram on the ball bearing, okay? But if we look at the lower surface, and I don't have it in front of me, so I can't remember exactly what it looks like, but it's like a lower piece that looks something like this, right? The ball bearing sitting right here. So in that case, we're only gonna have a force where we used to be in contact with something, right? So in that case right there, you're gonna have, well, I got the dropsies on the pens this morning, that's the second time. We're gonna have a force where we had contact for the ball bearing here, but that would only be the force at that point. The piece that's up here, we'll have a force at that point as well, right? And let's not forget, equal and opposite, everybody, right? So if you draw that force downward here, that same force has got to be going the other way on the other piece, right? Equal and opposite. To your question, which is a fantastic question, if we were drawing a 3-by diagram of the ball bearing, which would not, but if we were, then in this case, just like any other ball bearing, or just like any other 3-by diagram, we've got the object, and then we have forces at all points of contact. So I used to have a point of contact here, so there'd be a force there. I used to have a point of contact here, there'd be a force there, in that case. But for these things here that you're being asked to draw the 3-by diagram of, there would only be one. Does that answer the question? Perfect, perfect. And also, smart, good question. What are the questions? Now that we're starting to get some questions rolling, look at it, ask yourself. Anything, anybody? Yes?
On the pliers, the bottom handle kind of goes downward, but there's no dimension for how far it's going.
Let me grab my glasses, I'm gonna look at that, okay? So, great question, but I don't have it in front of me, so therefore, I gotta borrow your paper. Thank you. Well, what again?
The bottom handle kind of goes downward a bit.
Yeah. Good question, I'm gonna hand it back to you. So the question goes to the dimension of the handle itself. And correct me if I'm saying it wrong, okay? You've got a dimension showing where the pins are at. But we don't have anything that talks about how far below, right, on the bottom. Can I see that one more time? I want to take something here. Okay. So what's not there, folks, is dimensions, vertical dimensions from the pin like up to the surface where the ball bearing's resting. And there's also not dimensions from the pin to the lower surface of that piece of the jaw, right? And that's what you're asking about. It turns out, so they're not given and they're not needed. Okay, but thank you for that. That's also a good question. I think you had one.
Yeah, just a question. There's forces acting on the handles, so does that make the A and B a not force cover? Or
What a good question that is, right? So the blunt answer to your question is that has nothing to do with A and B. If I'm saying, can I borrow yours one more time? I gotta see this. Now watch, I'm gonna forget the whole thing. I'll be right here. Thank you though. So I want to double check before I answer you. Yeah. Thank you. Perfect. I appreciate that. So to your question, the 150 Newton force is actually applied on the handle, but not on member AB, right? So member AB has a grand total of 2 pins,
yeah.
no weight and no applied forces, and you called it a 2-force member. Boy, I hope all of you were listening, because that's a 2-force member. Good catch. See, that right there, folks, that just made this whole thing a lot easier, right? Yeah, fire away.
So
Okay.
that is
let me see what you're asking me again. I just didn't hear you well. Well, I'm going to expand the question, okay? And I want to make sure everybody hears it. So the question has to do with pins C and D, right? And I think what you're asking is, how are we representing forces on those pins? Are moments involved, right? So this goes to, again, let's make sure, and I'm so glad you asked this question, because one thing about this particular problem is the picture looks different than what we're so used to seeing. We're so used to seeing pins. You see me draw them up here, like a little thing with a little hole in it, and voila, that's a pin, right? Just like we're going to see a bunch of pinholes in this thing up here, right? What's important is a pin is a pin, right? And we know with pins, with all pins, X force, Y force. And if it's smooth, no moment, because there's no resistance to rotation, right? So that is a smooth pin. There can be no moments on that pin. Make sense? Good. Good. And folks, that will be one of those things too that I think you'll see it more when you're actually drawing out the free-body diagrams. But just remember, the rotation about a smooth pin, since there's no resistance, there can't be a moment there. Yeah, far away.
And this points C and D, maybe you can't answer, would that also be two force members because there's two pins into this?
C and D. I'm going to borrow it again. Well, and it's also a great question. Let's go back to our rules on two force members, right? So the component has a grand total of 2 pins. For that part, check. The component has no weight, check. The component has no applied forces. There's a force on where the ball bearing touches that. So that would be a force. So therefore it can't be a 2 force member. But that is a great question too. See folks, these are good questions. These should be helping you figure out how to do this. If I'm you, I'm taking these notes all day long because it's gonna play later on. What other questions? Now they're rolling. What other questions have you guys got? Nothing more? I'll do this. Going once, going twice. Anything, anybody? All right, we'll move on past that then. So now, and again, to all of you that ask those questions, they're great, and I appreciate them. And whether you know it or not, those questions helped out everybody, so they're greatly appreciated. So now back to this. We're moving into the world now of machines. We saw frames the other day, and if you think about what we saw with frames, gosh, I just want to think about this. What you saw with frames, almost in the context of, you guys remember the cam crusher on day 1? Well, guess what we're going to end the day with? We're going to do the cam crusher problem again. I told you to see it again. We're going to see it again. But in the spirit of the cam crusher problem, on the first day, we saw that the way to solve these problems is to choose items to make free-body diagrams out of, and with each of those, we solve free-body diagrams until we get to the thing we want. And in the case of the frame problems that I showed you all on Monday, what did we do? We saw the problem, we choose something to make a free-body diagram out of, applied equations of equilibrium, and voila, we solved the problem, right? Now we're moving into machine problems. In fact, the problem that you've got on your midterm is a machine problem. And you know what we're gonna do different here? Absolutely nothing. We're gonna make free-body diagrams, apply equations of equilibrium, and solve the problem. So it's like, okay, well then what's the difference here, man, between the frames and the machines? Nothing. The difference being, again, that, hey, if I take a machine and throw it at you, it's gonna have a different shape when it lands versus a frame will not. That's literally it. But the approach is the, okay, let's check into the nothing's new here department one more time. The approach is free-body diagrams, solve equations of equilibrium. There's just nothing new here. In all of this, and as you guys are seeing on the midterm right now, I'm believing that at this stage, you're all starting to really buy into the idea of, like, you know, on day 1, he said this is all about, we gotta be able to draw free-body diagrams, and guess what? It's all about drawing free-body diagrams. Check this one out up here. This is a machine problem. One might argue it kind of doesn't look like a machine problem, because wouldn't this, if I actually threw this at you, have the same shape when it landed? No, it wouldn't, because of these two pieces right here. They are free to rotate. So it's not technically a frame problem, although, boy, it's not going to look any different when we solve it. This one goes like this. The clamp is adjusted so that it exerts a pair of 200 Newton compressive forces on the boards between the swivel grips. In other words, this thing here is being adjusted by twisting this threaded piece here, adjusted so that this is coming together and squeezing these two boards right here with a pair of 200 Newton compressive forces. The ask on this problem, folks, is determine the force in the threaded shaft BC and the magnitude of the pin reaction at D. We want to know what is the magnitude of the pin force up here on D, and also, how'd they say it here, the force of the threaded shaft BC. Those are the things we're being asked to do. Now, I want to cue this up by pointing out to you all that the problem here said nothing at all about smoothness or friction or anything like that. So it is imperative that we recognize that in the absence of that, when the author's silent on something like that, we assume everything's smooth. So even though we know that that's utter nonsense, the friction on these boards is certainly going to be more than zero, we don't assume that. We assume it's smooth unless we're told otherwise. So now it simply boils down to, again, we want to figure out the force in this shaft right here and the force on that pin right there. As you look at this, we already know we're going to do a free body diagram of something, or some things, or multiple free body diagrams of some things. What we don't know is how many free body diagrams we're going to have to draw before we get to the solution. And it's this particular problem, and I choose to start with this particular problem to point out that in looking at this, we see there's so many different possibilities. I could do a free body diagram, for example, of this whole thing with the boards taken out and simply show those 200 Newton compressive forces that would be there. And in that case, maybe solve something. Actually, if you think about this, if you did the whole thing and you just show these two forces right here, there aren't any things that are detached, so it doesn't really get you anywhere. So could you make a free body diagram of that? Sure. Is it going to produce any fruit? No. We could do a free body diagram, for example, of just the screw shaft. Absolutely. We could do the screw shaft plus this lower jaw right here. We could take apart these square things and draw free body diagrams of those. We could draw a free body diagram of this piece right here, or maybe this piece plus this piece. There are so many possibilities, so many. And the thing that I want everybody to make sure you hear is that if you make a choice of, you look at a problem like this and say, I think I want to start with a free body diagram of the threaded shaft, for example, right? If you do that and it doesn't produce any fruit, then hang in there, keep going. Don't give up, because there's so many other free body diagrams that you can choose to draw. Now there's a flip side to that. The flip side is the more we look at problems like this, the more experience we gain on working problems like this, the more likely you are to actually see that although you can pick a lot of different things to make a free body diagram out of, there's going to be one or two that makes the whole problem a lot easier. In fact, real easy in this case right here. Folks, a principle that we always want to keep in mind, I've talked about this before when it comes to free body diagrams, whatever you choose for your free body diagrams, you always have to have a free body diagram, or more than one free body diagram, depending on what it is, that shows the things you're looking for, right? If you are looking for certain forces, clearly we can't find those forces unless we have a free body diagram of something that features those forces, right? So think about this. We're being asked to figure out the force in this threaded shaft right here and the force on this pin right here. Now, if you look at this piece alone would feature the pin forces. This piece alone would feature the force in the shaft, right? So knowing that you've got to draw a free body diagram of something that features the forces you're looking for, why not start with that? Let's do a free body diagram of just this upper piece right here, folks. So following the same old, there's nothing new here rules. We start by just drawing a sketch of that thing, and it looks something like what I'm drawing right here. And I'm probably making that a lot not as good as I could. I want to just modify this a little bit right here. Comes down closer to something like this. And as I look at this, I've got a pinhole here at E. I got another pinhole over here. And I've also got a pinhole down here. Now I want to step back and look, did I really represent, I've got the piece itself, yes. I've got the pinhole here. This problem here is not clear at all, folks, but underneath that pinhole right there is clearly going to be something that is going to articulate with the threads of the shaft, like a nut of some kind. Not seen, but this is where we have to understand machines enough to know that there's got to be something there like that. But that's going to work out in the wash here. Let's not worry about that. That's coming up in just a second. Let me do a quick little fix right here, and there's a reason I'm doing this. I'm not being picky, but there's a reason, so let me just do that. That looks a little bit better. Okay. Now, so I got this here, the pin at D, and the pin over here at E. I did not include this piece right here. It is important to know that if you did include that piece, there's nothing wrong with that. There's nothing wrong with including that piece. We win either way. In fact, I'm going to go ahead, and again, as you can probably tell, this is kind of driving me nuts the way I drew this, so I'm going to try to make this just a little bit better here, folks, and there's a reason for it. If I bring this down here and I do that to make this look a little bit better now, if I wanted to, I can include the square piece on here that you see right here. There's nothing wrong with doing that. Why? Because once again, we can draw any free body diagram we want, any combination of stuff. The point I want to make sure you all hear, though, is whether I include this or not, for reasons you'll see in just a minute, it makes absolutely no difference whatsoever. No difference whatsoever, and we're going to see why in just a second. So in drawing my free body diagram, I have sketched my part. I am following the rule of including an X and Y coordinate axis system. And I want to make sure that we all note that from the original drawing, and the drawing is much clearer in the book, this line right here, this horizontal axis line, passes through the center of both of these pins. So the dimensions here apply to both that pin and that pin as well. Just want to make sure we all see that. So now, having said that, think about our rules for free body diagrams. We sketch the part, we add a coordinate axis system. If it has a weight, we include the weight. This has nothing to do, there's no known weights for this, so nothing there. We include any applied forces, right? Any applied forces. This doesn't have an applied force, technically, but below it, there was a 200 Newton, we were told there was a 200 Newton compressive force pressing down on the boards right here, right? So if there's a 200 Newton compressive force pointing down, then there's got to be a 200 Newton force opposing that. So that means that down here, we should show the 200 Newton force pushing back up on that surface right there. Now here's why I said a moment ago, it doesn't make a bit of difference if we include this square piece or not. The reason is this 200 Newton force, if we did not include the square piece, would be passing right through the center of the pinhole anyway. We could have just showed it on the pin and been perfectly fine, right? But we don't have to in this case here. We're showing it on that flat surface, so that's a win. So we got that. Now beyond that, let's think about this. Now we go through the same old, there's absolutely nothing new here, process of putting forces at places where we used to be in contact with something. Now, right off the bat, we should be clear that we also understand this is not a two-force member because, I mean, none of the boxes get checked here. There's 3 pinholes, so it's not a two-force member. Let's make sure we don't mistake that. So therefore, we got a pinhole there at D. Now the question becomes, is that pin, though, associated with a two-force member? We look at where it was connected to this piece right here. So this piece right here, 1, 2, 3 pins, so no, not a two-force member here. So if it's not a two-force member, and it's just a pin, pins are pins, right? X force, Y force. We don't have to think about that. So let's throw on now a simple, this is point D. So let's call this force here, we'll call this one dx. How about this one here at dy? And okay, so far so good. Now we've got what's going on down here at B. Folks, here's the secret sauce to this particular problem right here. In this particular case, it may not seem obvious, but I want to go back and talk about two force members, right? We said two force members, the requirement would be a grand total of 2 pinholes, no weight, and no applied force, right? We've also said it doesn't matter what the thing looks like. We have talked about two force members that could look like all sorts of weird curly shapes, and if it's got a grand total of 2 pins, it's 2 force member. Here we've got an object that has a handle, screw threads, but it has no weight, it has a grand total of 2 pins, and there's no applied forces on this. It's a 2 force member. So because this piece here is a 2 force member, we know that the force that must exist in this, and if you think about this, this is the axial force of the screw here, right? That's the axial force of the screw. The force that must exist on this would have to fall on a line that connects those 2 points right there, or the 2 pinholes. So in that sense and in that view, we would have a force drawn here, like so. Do we know really what direction that force should be? Kinda. If you think about this, when this is screwed together, that's trying to force this piece this way, so the reaction force would probably be going back the other way. So with that logic, let's throw that in like this. Let's call this one force BC, by the way, where BC is going to be the answer to the part of the problem that's asking us about the force in the threaded rod. So when we know BC, we've got half the answer done already. Now again, do we know this directionality? Not really. Do we care? Not really. The math's going to figure it out for us. But folks, I want you to just take a moment there and take that in. This problem, which looked pretty busy when we started with this, right? By selection of one free body diagram, that free body diagram features the force in the threaded member that we're looking for. We're going to be able to get these 2 things here and figure out the magnitude of the force on pin D. Those were the 2 asks, specifically the 2 asks of this problem. And if you step back and look at your free body diagram, you got one free body diagram with a known force on it and 3 unknowns. We got a budget of 3 equations in the bank for solving the 3 unknowns. One free body diagram is going to solve this problem, just like that, just like that. So this again, this is where you got to look at this and say, did I see anything there that's new? The answer is no. Nothing's new here whatsoever. So even though we're advancing ourselves now into more complicated problems, if we're doing this right, we're looking at them and it's like the complexity doesn't bother us because we just know there's just nothing new here. So now, having said all that, and by the way, it is worth going through the mental check box of did I cover everything in my free body diagram? Am I really confident in that free body diagram? And again, go through it. You know, did you draw a piece of 2 seconds? I'll come to you. Did you draw this thing out? Yep. Did you include that? Yep. Applied force? Yep. Pin force here at a place I used to be connected to something? Yep. The 2 force member? Yep. Was I connected to anything else? Did I touch anything else along the way? No. That's a complete, and we should be confident, free body diagram. Yes, question? Say again for me. Pin E. Oh, good. Oh, what a great question. So I'm going to repeat it so I want to make sure everybody hears this. Okay? The question was, well, should there be some forces here on pin E? The answer is no. There shouldn't be. And why? Because remember, we only show forces, hear me when I say this, folks, we only show forces where we used to be connected to something. Pin E is still connected. So that's a wonderful question. And I say it's a wonderful question too, folks, because that particular thing right there messes with people. It's not at all uncommon when you're learning how to do these kinds of things and learning how to do free body diagrams to put forces at a place you think there should be something there, when in fact there isn't. But if you buy into the idea that I never put a force anywhere except where I used to be in contact with something, then you'll be all right. Yeah.
So if you took the one out, if you took that one part out, and then
Yeah, good question. So, and it's Nate, right?
yes.
Nate's question. If the block wasn't here, would I be showing a force here on the pin? Yes, indeed, if the block wasn't there, because now the pin used to be connected to the block. And further to your question, the question then becomes, well, what would that force look like? Now, here's where it gets a little funky, because you might look at that and say, well, that's a pin. I'd have a Y force and I'd have an X force here, right? But that's where, in that case, you would have to come back and say, okay, I got too many unknowns. Now I'm going to have to do a free body diagram of maybe just that block. And that free body diagram of just that block is going to show you only have a Y force here. So, you know, you'd still get it, but it takes now a couple free body diagrams to get there. Great question. Yeah, fire away.
I know you said that this isn't a two force number, but does the shape it has between point D and E matter?
Between D and E?
Yeah, the bend rather than anything else. Like could you draw it as just like a straight linkage from D to E?
Yeah, I think so. But I want to make sure I understand your question. You're referring to this piece right here, right?
That bend, yeah.
Yeah. So just to be clear, it's not going to be a two-force member anyway because it's got 3 holes.
Yeah.
But I think what you're saying is, if this really was a two-force member, could I solve it by not even drawing this, but just drawing a straight connection like that? Yeah, the answer is yeah, because again, we don't care what the shape of the two-force member is in between the pinholes. We just care about the pinholes, right? So you can do all sorts of bizarre stuff in between here and there. The only downside of doing that is now you're trying to convey something visually, though, that doesn't match the actual problem. And so remember, part of our job is to convey what we're talking about visually. It's a good question, though. What other questions we got over here? Anything, anybody? All right, sweet. Again, all great questions, everybody. Let's solve this problem. So now if I look at my free body diagram, now I'm just going to go to the same old, there's nothing new here. You might ask yourself before you do this, though, is there a scenario where I get to solve this in less than 3 equations, maybe even 1 equation? Well, in this case here, we actually need to know all 3 of these forces. So if I need 3 forces, I got to use 3 equations. So let's sum forces in the x direction. Let's look at this, folks. And now one last time here, and I'm going to stop emphasizing this because I think it's time to stop emphasizing this. But if what I'm about to do here in writing out the sum of the forces equation, if you're looking at this and you're like, I'm not sure why he's doing that or how he's doing that or whatever, if you're at that point, you got to get past that point, folks. We're so far into this right now that what I'm about to show you should be just second nature. Why am I going to write here, for example, dx? Why did I write dx versus minus dx? Why am I going to write now minus bc? Why is that minus? Why isn't dy and 200 in my equation? Those kinds of things. I've had people literally, honestly, folks, I'm telling you the absolute truth when I say this. I've had people this late in the course look at an equation like that and say, I don't know what it's equal to. They add to 0. Okay, let's make sure we understand that. So dx minus bc, dx positive x, bc negative x has to be equal to 0. We don't solve that. Sum force in the y equation, right, or direction right now. So looking at that, I see dy as positive. I see that 200 is positive, so plus 200. I don't see any other x direction forces, so that's equal to 0. And I know I can solve that. In fact, right now I know that dy is going to be equal to minus 200 newtons. And the minus 200 in this case tells me that my wild guess for the directionality of dy was wrong. It's actually going downward, no problem. But I've got a choice. Let's remember this too when we're solving. I have a choice of I can go back now and I can change the directionality of that arrow and make that value 200, or I can keep the directionality the way it is and keep the value at negative 200. They are the same. We just got to make sure whatever choice we make, we got to carry that through our mathematics. So keep that in mind. I'll come back to that. So now I got to sum moments about something, and we're always going to remember that counterclockwise symbology right here. And yeah, again, folks, I will be looking for this on the midterm. Did you use that symbology? And now it's a question of, all right, some moments about what? D is a great choice here. If we choose D, then we get dx not in that equation, dy is not in that equation. We'll have only one unknown in that equation. It's going to be bc. So let's do the moments about D. And let's see here. So with pin D being our moment center, looking at BC the way that we drew it, we should see that BC is going to be doing a clockwise rotation about D, so therefore it's negative because of the clockwise convention. So minus D BC times the moment arm. The moment arm being the distance from pin D down to the line of action of BC, which is going to be, we look at this right here, these are on the same plane, so 10, another 10 is 20, and 30 is 50, down to there. So my moment arm is going to be 50. And then I got that 200 over there. That's doing it counterclockwise, so that's going to make it positive. So plus 200 now times its moment arm, which is going to be the distance from D over to the line of action of that 200. So I'm seeing right here 35 and 40 gets me to 75. And that's that. Those are the only two pieces that are going to be on our moment equation. Let's solve this, setting that equal to 0. We should see now that BC is going to be equal then to 200 times 75 over 50, and that works out to be about 300 and something, about 375 newtons. And that worked out to be a positive number, so we know our assumed directionality there was correct. Yeah, fire away.
Would that not be 300? 200 divided by 50 gets you 4 times 75 is 300.
Yeah, good. That's a good point. Now, why do I have it written down? Oh, you know what? I actually looked at the wrong thing. That's why. Thank you for that. All right, hang tight here. I'm gonna double check something because I do have 375 written in my notes, but that doesn't mean I actually like it. Yeah. I see what's wrong here. So folks, and this is on me, I want you to understand, this is on me. We're gonna stick with what I've done here, okay? But the original drawing, which I didn't see when I drew it up, the original drawing had this pin, no, wait a minute. Oh yeah, wow. Again, totally on me, folks. The original drawing has pin E up here, but pin D is on the same line as the interface between them. So this should have been a 40, and that's why my numbers in my notes are not lining up. But I drew it wrong. I'm gonna live with it and own that. So in that case there, let's fix this, and that was a great catch on your part. But if we put a 50 into this, then that 50 now gets us to, as you point out, 4 times 75 is what, 300 as you said. So let's change that to 300. That means the notes go out the door here. Okay, so fixing that now to 300. And now that we know that that is 300, then we can come up here. That makes dx also equal to 300 based on that. And then the final ask here was the magnitude of the force on pin D, and that magnitude, of course, just like we saw the other day, D then would be the square root of dx squared plus dy squared, and that would be the square root then of 200 squared plus 300 squared, and whatever that works out to be, that's going to be our answer. And there we have it. Again, thank you for that catch. That was just me not being able to see the problem as well as I would like to in my older age. But anyway, the most important takeaway of the whole thing, though, folks, was again, whatever our free body diagram is over there, we work with that, equations of equilibrium, problem solved. Check it out, folks. I really want you to think about this. Check it out. We just did a machine problem that, upon first glance, might have appeared to be a little bit challenging because there's a lot going on there, right? And instead, we looked at it, we made one smart pick of one free body diagram, 3 equations later, we're out of this thing. That is machine problems. That's the thing that we want to gravitate towards. Like, hey, these things are not that hard. They look harder than stuff we've seen before, but because, again, there's just nothing new here, right? Was that a dragster or something? I didn't get to see what that was.
Mini bike.
What?
Mini bike.
Mini bike. That's different. All right. The only thing I haven't seen so far in this university in all my years is somebody riding a horse down the hallway. But if I think about it long enough, probably I have seen that. But anyhow, that's the takeaway I want you all to have. There's just nothing here that we have not seen before. Questions on this problem, anybody? Questions? Yes? Junior?
The dy equals negative 200 newtons. You add positive 200? Is it because it's now in the x direction instead of the y direction? Or why did you change it to be positive.
Where did I change it?
dy is negative 200 newtons.
So here, it was originally dy plus 200, right?
Uh-huh.
And so that was
Oh, you
because
swapped it.
both were positive directionality. But of course, when I slide this over to the other side, the equal sign's gonna become negative, that's why.
Okay.
Does that make sense?
Yeah.
Okay, good stuff. Anything else, anybody? Questions about this one? Okay, cool. Your turn.
So tired.
Let's do the can crusher problem. We'll talk through it, but I want you to draw out the free bodies that you think. Let me get this drawn up here, folks, because we'll remember this has some busyness to it. There's a lot of stuff going on here. Let me draw this all out. Well, folks, there we have it. Here is the same problem we saw back on day one of this course. We've already seen it get solved one time, so maybe our memories are going to carry us, and then just we rely on that. But if not, let's just go and remember what this was all about. We have a can crusher here that, in the position that it's shown, if 20 pounds is applied to the handle, pulling up on the handle here with 20 pounds, what we want to figure out is what is the force crushing down on the can here. The can's being crushed. What's the force on that? So I want you to work at your pace. I'm going to slowly talk us through this, so don't wait for me if you don't want to. But so we know that we're going to end up figuring out what the force is right here. We also know, though, that we need to use, or at least have one free body diagram that shows an applied or a known force. If we don't include the applied and known forces, then they don't get factored in. So just like we saw on day one, there's a lot of different possibilities here for things that we can do free body diagrams of. And now today, I would expect that literally everybody in this room right now is looking at this thing, and we've already bought into the idea that one of the first things we want to do is hunt for two force members, right? So everybody should see 2 force member here, 2 force member here, 2 force member right here. We saw them on day 1, but now we know how to find those 2 force members. Where do we start? Folks, I would start with a free body diagram of that handle. Why don't you do a free body diagram of the handle if you haven't already started it? Let's do that. So you do yours. I'm gonna slowly draw a version up here, and then I'll fill in some gaps as we go. So again, take a moment, do the free body diagram of this as you see fit. And I'll wait a minute here, then I'll kick in and start adding some stuff to it. Folks, as you're doing your free body diagram, now obviously we need to have the applied force on here. So here's our 20 pounds sitting back here. We've already asserted that DE is going to be a 2 force member, right? So if DE is a 2 force member, then that means the only force that can exist on pin E has to be the single force associated with DE. We don't need to know its directionality, but let me just say we know its directionality. If you think about this, if I lift up on this handle, this piece here is compressing this 2 force member. So if it's compressing the 2 force member, then the reactive force is going to be pushing against that. So a single force DE would be drawn on the free body diagram like this. Now, this piece by itself is certainly not a 2 force member because it has an applied force on it, right? That means that even though we represented single force DE, 2 force member DE here, that's just a straight up old pin. There's nothing new on that one, it's just a pin. So that means I'm gonna have some, I don't know, maybe there's an FY going down like so, and then some FX maybe going off this way. Now folks, if what you did when you saw this, instead of you're drawing your own free body diagram, if your free body diagram looks like that, that's the right free body diagram. Now, that doesn't mean that your arrowhead has to be pointing this way. It doesn't mean that these arrowheads have to be pointing this way either. I'm only pointing them that way because that's the way I'm seeing it done, but your math is going to straighten us out anyway, so we're not worried about that. Now, if what you drew for your free body diagram doesn't look like that, now is the time to make sure you're looking at this and saying, okay, what did I not know? What did I miss? Right? What are the gaps in knowledge that we need to fill in? But that's what it should look like. Now, having said that, we go now to, all right, what do we need to solve for? Now, folks, that free body diagram has 3 unknowns in it, right? We got 3 equations in the bank. We can solve for all 3 of these forces. But here again, do we have to? In this case here, we certainly need to know the force in DE because we're going to carry that force through and work our way down to this plunger, right? We're going to carry this one through. Do we really need to know what Fx and Fy is? No. If we solve for them and get them, does that hurt anything? Certainly not. In fact, I think we all can look at this. Right now, I think we're all in a place where even without doing the equations of equilibrium, Fy is going to be 20. Fx is going to be whatever DE is, right? So we can solve these quickly, but again, we just don't need to. All we care about is DE, and in that case there, we get that with 1 moment equation, right? So the single moment equation, if we choose to use point F as our moment center, then Fx is not in that equation and Fy is not in that equation. So it would give us the one thing we do want, and that's DE. So let's look at this. So DE with respect to point F would be doing a clockwise rotation, therefore it's negative. So minus DE times its moment center, or I'm sorry, moment arm, not moment center, the distance from the moment center to that force, which we see right here, given to us in the original diagram is 8. So DE times 8. And then I'm going to step back and take 10 seconds. I want you to fill in the rest of that. Fill in the rest of that moment equation, folks. Make sure you see it.
Minus
So once again, Fx is not gonna be in that moment equation, and Fy is not gonna be in that moment equation. But the 20 pounds will be. The 20-pound force with respect to point F is gonna be causing a counterclockwise rotation, therefore it's gonna be positive. So we'll have plus 20. And then we gotta multiply that by the moment arm, and we should all see from the original diagram that the moment arm on that's gonna be 30 inches in this case. So 30 here. And folks, that completes the moment equation. We just know that this is all gonna add up to 0. And as we pause there a second ago to give you the opportunity to fill in that moment equation, once again, if you didn't see that at this stage of the game, you gotta see it. So that means there's work to be done here if that applies to you. I'm hoping it doesn't. But make sure you see where these moment equations come from, folks. And again, I know I'm beating a dead horse, but you gotta understand when I say make sure, understand I'm saying you need to make sure to succeed in this course and for everything you're gonna do in your future. If you don't see it at the end of this course and you go into your next course, you got no chance. So you wanna make sure you see this and understand it, folks. If there's gaps, let's work on that. Solve it. So in this case here, folks, if I solve for DE, realizing that DE here, when it slides over to the other side, the equal sign is gonna become positive. So we're gonna have DE then being equal to 20 times 30, which is 600. We're gonna divide that by 8, and that's gonna be 75. So right now, we know that the force in DE is 75 pounds. Now, to continue on, we now know what DE is. The question becomes, what's our next free body diagram? We haven't solved the problem. We know that ultimately we're gonna do a free body diagram that's gonna show the force that we're looking for. The question becomes, do we have enough right now to actually do that? And the answer is probably. But let's not try to get too fancy with this in here, folks. You may remember that when I did this on day 1, I talked about the idea, this is the first time I talked about the idea, we can draw a free body diagram of anything the heck we want to, right? So in this case here, to me, the right play is to draw a free body diagram of pin D. So let's do that. Let's do a free body of pin D. Let's just take a minute. Let you kind of sketch that out first, and then we'll come back and we'll do it up here. So again, take a minute, sketch out a free body of pin D. So not to jump too far ahead here, folks, but as we're drawing now the free body diagram of pin D, note that I've added in the force from the two force member DE. And folks, here you'll notice that I drew DE going to the right here. I'm drawing DE off to the left here. That's not because, although it's related to it, but it's not because I drew it that way over there, but it's because if we look at the original piece, if we look at DE, we would see that member DE would have forces applied to it that are compressive forces, right? So those forces would be looking like that. if we look at the right-hand arrow here, it's this pin that associates with, or it's that pinhole that's associating with this pin. So that arrow there drawn to the right has to be drawn to the left over here. Now, however you did it for yourself, we should also contemplate that we have a force in member BD, which is also going to be a compressive force and therefore drawn into the pin. And we also have the same thing going on up here from member, two-force member by the way, CD. And that right there is the entirety of what our free body diagram, our pin should look like. The only thing you could add here, folks, is you could add in the angles. So 67 there, 78 up here. Again, not necessary to add these things to free body diagrams, but certainly doesn't hurt. So now, two things with this, folks. This free body diagram here is correct. However, there's a nuance. We already know the value of DE. So it would not be smart to put a unknown here when you already know the value. In fact, you might look at this pin and say, there's 3 unknowns right there, and I only have 2 equations to work with on this one because all these forces are concurrent, right? So there's no moment equation on this one. Wouldn't it be easy to look at this and say, I can't solve this because I got 3 unknowns, when in fact you don't. You already know what the value of DE is. So we knew it was 75. Let's come back in here and let's make this 75 right now. So 75 pounds right there. Now we're in position to go ahead and let's solve for the unknown forces here. So if I sum, we should do the same here. So let's sum force in the x direction, folks. Let's just take a minute. I'm wanting to encourage you all to do this here, so I'll shut up for 2 seconds. I'm just going to ask you to write out your version of the sum of force in the x equation here. Folks, so your equation should look like this. Let's just kind of go around the horn here, starting with BD. So BD is tending towards, I've drawn my XY axis over here. BD is tending towards positive X, so that's going to be, in this case here, BD times the cosine of our angle 67. So you should have BD cos 67. CD is also tending towards positive X, so that's going to be a plus CD cosine of 78, and then minus 75. As it's purely x directional, so therefore there's our x equation right there. And obviously we have 2 unknowns, and 1 equation can't solve that. So let's knock out the sum of forces in the y equation. Once again, I'll take just a few seconds on this one here, folks, if you haven't already done it. Let's do sum of forces in the y direction. This one should be pretty quick here, folks. If we look at BD, that one's tending towards positive y, so that one's going to be BD times the sine of 60. Hold on a second here. Yeah, sine of 67. And then CD, that's tending towards negative y, so minus CD times the sine of, in this case, 78. And the 75 doesn't show up in this one, so we set that one equal to 0. So there we have it, 2 equations, 2 unknowns. We can solve for either one of these right now to get the 2 unknowns. The way that I would do it, folks, if it was me, since ultimately I don't care what CD is, I only want to know what BD is. Even though I can solve them both, I just don't need to. So I'm going to solve this equation right here for CD as a function of BD. And in looking at that, we should see that CD ends up being equal then to BD sine 67 divided by the sine of 78. And with that, I can substitute this in right here. And I'm going to bring this up somewhere else over here. So now I'm going to have, this becomes BD cosine 67 plus the substitution for CD. That's going to be BD sine 67 times the cosine of 78, all divided by the sine of 78. And I'm going to swing this 75 over the other side of the equal sign. I'm going to make that equal to 75. So folks, as you see in that equation right there, I won't go through the pain of solving it more, but what we'll have here is when we take all these terms and combine them, we'll have BD times the cosine of 67 plus these three terms is equal to 75, so we'll divide the combination of these out. And when we're all said and done, we're going to find out that BD ends up being equal to about 128 pounds. It's like 127.95, but 128 is perfectly fine. So now we know the value of BD, and we're down now to the last step to solve the problem. Think about what we've done here, folks. We've done two meaningful free body diagrams. The one up there on 2 force member DE is, you know, we didn't need to do that, but we did it for clarity. Two meaningful free body diagrams has got us to the point now that we know the force in this 2 force member BD right here. So I went ahead and did the free body diagram of the plunger. All right, we've seen this before. The plunger by itself is going to have the force on the can being applied to it. We have contact force on the left side of the plunger, which we really don't know if it's there or not because the problem was silent on it. But we can assume it's there because it's going to turn out it doesn't matter to us anyway. Force on the can, force right here in BD. I purposefully did not draw the direction of this arrow right here because I want to have it here first. So pointing upwards right here, we're going to be pointing downwards over here. And a couple of things about that. First of all, we already know its value from what we just figured out over there a moment ago, 128 pounds. So we got 128 pounds right there. And then as far as this directionality goes, this angle right here is going to be the same 67 degrees. That angle right there and this angle right here have to be the same. So now as we look at this, folks, and this is the reason that the side contact forces didn't matter, and the fact that, again, we're silent on whether or not they even exist. All we need here is one force equation to solve for the force in the can. Yes, question?
Would it be wrong to not include the side forces?
Yeah, in this case, it wouldn't be wrong. And that's what a good question that is. So let's unpack your question. The problem statement, which I didn't give it to you formally, but the problem statement is completely silent on whether or not there's actual contact being made here on the sides. We just don't know if there is or isn't, right? If there's no contact, then there are no forces here. We know that. As a matter of fact, let's cement that one into our minds, right? If there's no contact, there's no forces. On the other hand, if there is contact, then what do those forces look like? Well, if we assume that the surface here is smooth, which again, we always assume it's smooth unless we're told otherwise, then the only contact force would be a horizontal force. We use the old rule here. If I tried to move this way, would I face resistance to motion? No. If I try to move it this way, would I? Yes. Right? So I would have a force here and a force over here, which is what I represented. But to your great question and point, do we even know that they're there? We don't. So if you did a free body diagram and you didn't include those, would it be wrong? Not at all, right? We just don't know. But I put them there in this case to say, even if we assume that they're there, the math lets us get around that. We don't need to worry about it. Good question, though. So now with that, folks, as we look at this, we should be able to see that we're now down to one final step. If we sum up forces in the y direction, we have F can drawn in the positive y direction as we see here, minus 128 times, in this case, what would that be? That'd be the sine of 67, and that's equal to 0, which means that F can is going to be 128 divided by the sine of 60. Oops, I'm sorry. F can is not, I started to do this wrong. F can is simply 128 times the sine of 67, and that's going to work out to be about 118 pounds. And that right there, folks, solved the problem. When we got together on the first day of this class, and we saw this exact same problem. I worked through a process in which I drew these free body diagrams. I did a lot of hand waving and a lot of, oh, it's all going to be clear to us in a few weeks. The question now is it clear these few weeks later? As we have now just done the same thing. Now, everybody in this room should be at the point of when I drew a free body diagram of this handle, all those weeks ago, now what, 7-ish weeks ago, when I drew a free body diagram of that handle about 7 weeks ago, now we should be at a point where everybody can look at that and say, yeah, I get it. I see exactly why you did it that way. Why you drew the handle to look like the handle. Why you added that XY coordinate axis system. Why there was only one force on DE, but there's 2 on F. We have FX and FY down there. But now we should all be at a point where it's like, yeah, nod the head like, yep, that's what I would have done, or hopefully that's what you did do, right? And now we can look at that and say, all right, now 7 weeks ago I said, hey, it's going to become clear in a little while, but we're going to have these things called moments. We're going to use this equation right here to figure out what the one force we care about is. Now we should all be in the same place of, yep, check, got that. Now that we knew what DE was, we should realize, okay, I can combine anything I want, but I like a free body diagram of this right here. Now we know why. And now we know that applying that one that we just figured out, let us solve for the one we need down here. This led to one final free body diagram, which led to the problem. What we saw 7 weeks ago should have left a lot of, yeah, I see it, but not sure why you did that, not sure why you did this kind of thing. Now we should be at the point of like, I don't even need you to tell us what to do. I know what to do. That's what I'm hoping we're at. What questions, folks, do you have on this problem now that we've seen it the second time? Was there anything ambiguous for anybody? They want to fill in a gap, fill in a hole? Sweet. Let's call it a day. Folks, you should be in good position now to do that midterm. Don't forget though, we're not going to see each other between now and due date, right? But I'll be watching my emails. So if you have something, shoot me an email. Don't hesitate to ask questions. Otherwise, I'll see you guys in a week. Have a good long Labor Day weekend.